So percent uncertainty, that is basically an error. Okay, so percentage error is actually given by absolute error divided by true value, and then you multiply it by 100%. This true value is the measured value. So our absolute error is the uncertainty, and that is 0.2. The measured value, you can see there is 100. And then you multiply this by 100%. Just make sure that these guys are in the same unit so that the unit can cancel. So this is going to give us 0.2%. So that's the D. The second one, we also want to calculate the percent uncertainty for a 150 cubic centimeter burette with uncertainty of 0.05. So that again, percentage uncertainty, which is a percentage error, is equal to uncertainty, which is the absolute error, divided by measured value, or the true value, and then you multiply that by 100%. So this is going to give us the uncertainty is 0.05, the measured value is 50, and you multiply by 100. 50 into 100 is 2. 2 by 0.5 is 0.1. So our answer there is A. Number 2 is saying a chemical reaction is of zero order when the reaction rate is, so what the question is saying, a chemical reaction is of zero order when the reaction rate is, what should be the reaction rate for you to have a reaction to be zero order? So what you need to know about the orders of reaction is that for zero order, the rate is equal to the rate constant. That's all. For first order, the rate is going to be equal to K multiplied by the concentration of reactant raised to the power 1. For second order, so you see that is basically how they all go. Very simple, isn't it? So second order, the reaction rate is equal to K multiplied by the concentration of the reactant raised to the power 2. You can as well determine their integrated rate laws, but for here, of course, we are not using integrated rate laws. But it's another thing that is important for you to know, the integrated rate laws for these reactions. Integrated rate law just relates the concentration of the reactants and products, actually just the reactants at the beginning. So it will give us the relationship between the concentration of the reactants at the beginning and at a point in time with the time. Okay, the relationship between concentration and time. So for a zero order, the final concentration or the time, the concentration at a specific time is given by the initial concentration and then minus kT. Normally we want to start with a kT and then we write the concentration. The reason as to why we write like that is because we want this to be in a linear form. So kT plus initial concentration. such that the graph for this one looks like so, where this is in the form y is equal to mx plus c. So you can see that the gradient is negative, that's why the line is going downwards. Y is representing the concentration, and then the x value is being represented by the time. When you come to the first order reaction, for it the integrated rate law is going to be final concentration is equal to this one is actually given in terms of exponent. So you say natural log of the final concentration is equal to negative kT plus natural log of the initial concentration. It's the same as the first one for zero order, it's just that you put natural log. So even on our graph, the graph will still be going downwards. But the difference is that on the y-axis has got natural log of the concentration instead of just the concentration. And then for a second order, it is the same as the first one, except you have 1 over the concentration. And the gradient, instead of being negative, it is positive kT. Even here it is 1 over the initial concentration. So for this one, when you are graphing it, because the gradient is positive, this line goes upwards. The y-axis is still, the x-axis is still time, but the y-axis you can see is being represented by 1 over the concentration. So you need to know this. This is important for you to know. Another important thing that you need to know about this is the half-life, the equation for the half-life. Half-life is the time it will take for the concentration that you have to decrease by half. So if you have got a concentration of 100, for it to reach a concentration of 50, what should be the time it would take? That is what we call half-life. For a zero order, the half-life is given by the initial concentration divided by 2 times the equilibrium concentration, or the rate constant actually. So you can see that zero order, the half-life depends on the concentration and the rate constant. When it comes to a first order, the half-life is equal to natural log of 2 over k. Sometimes you just see, because natural log of 2 is 0.693, so just see 0.693 over k. So that tells you that for a first order reaction, the half-life doesn't depend on the concentration of the reactant. For a second order, the half-life is 1 divided by k, initial concentration of the reactant. This tells you that the half-life will decrease if you increase k or if you increase the initial concentration. So please, these equations that I've written here, all of them are very important for you to know. Okay, so the question is saying a chemical reaction is zero order when the reaction rate is, where they've given a Ca being the concentration of the reactant. So what does this tell you? When you're talking about the concentration of the reactant, look at this. Zero order is this one. Can you see it in the rate? No. So the reaction rate doesn't depend on the concentration of the reactant. So for this question here, there is no answer. There's no answer for this one. Okay? Because all of these are telling you it is proportional to the concentration, proportional to the inverse of the concentration, proportional to 2 over the concentration, independent of temperature. Now, temperature affects the rate of the reaction, whether it's first order, second order, third order. Number 3 is saying, in the following reaction, for iodination of propanone, there is an increase in concentration of ions. So the equation, the reaction has been given. Which of the following techniques is not applied to follow the progress of the reaction? So remember, there is increase in concentration of ion. So when ions are changing, what technique can you use to follow how the reaction is going? Calorimetry measures the energy in a reaction. Okay, that is about calorimetry. Conductivity, for it, you are going to be measuring really the change in the ion concentration. Now, remember that is concentration, and the question is saying what are you going to be? What technique will you be able to follow up when you're using the concentration? Conductivity, it is the ion concentration. And then pH, you measure pH by looking at the concentration of hydrogen, that is still concentration. Back titration, it is a titration. A titration, you use the concentrations. So the answer here is calorimetry. Which of the following techniques is not applied to follow the progress of the reaction? So calorimetry, you don't really use the change in concentration, because what you use is the changes in energy. Okay. Number 4 is saying, in iodine thiosulfide titration, indicator is added at the start of the titration, equivalent point when solution turns straw yellow, point when solution turns blue black. When you are doing this titration between iodine and thiosulfate, the indicator that you put, we call it the starch indicator. Starch indicator. This indicator is added after most of the iodine has reacted. So added after most of iodine has reacted. But the question is why? So this is because when that doesn't happen, the indicator, which is iodine, remember iodine is a test that we use for starch. Okay, so this iodine is actually going to be reacting with the starch, and that is going to affect the reaction. So I want to add the starch indicator later on after the iodine has reacted. And how would you tell that the iodine has really reacted? So you are going to see a straw yellow color. Okay, that is going to be the color. And at that point, you now add the indicator. Color of starch iodine complexes. Now, this is something you've been doing from, I think, grade 8. Blue, black, blue, black, blue. The test for starch. Number 6 is saying, in an experiment, it was observed that at the concentration of one of the reactants was doubled. Okay, as the concentration of one of the reaction was doubled, gradient of the graph also doubled. Okay, remember the gradient of the graph represents the rate. If you have got time this side, you have got concentration this side, and then you have got a graph like that. This is representing the rate. The order of the reaction with respect to that reactant is, now, if the concentration and the rate differs by the same factor, it means that that's a first order reaction. How do you determine the order? So rate is given by K multiplied by the concentration raised to the power n. For here we've been told that if we double the rate, so let's say it is now 2, let's say the rate is x, rate is equal to x, so it will become 2x is equal to k. Remember the concentration also doubled. Okay, So that is going to be 2 times the concentration, and then she raised to the power 2. So here you can actually, let me remove the way I've put it like this. It will mean something different. It is a concentration that we are raising to the power 2. Okay. So at this point, you can see that if you divide it through by 2, oh, by the way, I'm saying this thing is raised to the power n, not this 2. I don't know where it has even come from. Remember, we doubled the concentration. So where there is A, we have doubled the concentration. So we're putting twice A. Okay, that is how it becomes. We are going to split the n in this case. So it's going to become 2x is equal to k, 2 to the power n, and then A to the power n. And then at this point, remember x is representing the rate. So this can become 2 times the rate is equal to, I remove the 2 to the power n, and then we have got k. Okay, so we have got k, and then we have got concentration of A raised to the power n. So you see this term here is the same as the initial term, and then this term here is basically this term here. So we're going to be now dealing with this because they're supposed to be equal to the initial term. So we're saying 2 is equal to 2 to the power n. This tells you that n is equal to 1. See, n, we call it the order of the reaction. So this is a first order. But you didn't even need to do this. Just know that for a first order reaction, when you double the concentration, the rate doubles. You triple, it also triples. For a zero order, the concentration doesn't affect the reaction. For a second order, when you double the concentration, the rate will increase by a factor of 4 because we raise it to the power 2. I hope that's okay. Number 7 is saying, please feel free to ask in case you are not okay. In iodine clock reaction,
So, could you please explain what you meant by what happens to a second order reaction when you double the rate?
so when you double the rate
Yeah,
of a
sorry, just
second,
for the concentration.
okay, when you double the concentration of a second order reaction, the rate is going to increase by a factor of 4. Because remember, for a second order reaction, rate is equal to K, the concentration raised to the power 2. So what this tells you is that if I'm doubling the concentration, this is going to be K, the concentration has doubled. That is raised to the power 2. So this is going to be K times 4. So you can see that the rate has increased by a factor of 4. If you triple the concentration is going to increase by a factor of 9 because it's going to be 3 raised to the power 2. Does that make sense?
Yes, it does. Thank you.
All right, great. In an iodine clock reaction, if the time required for color change is too small, then percentage error with respect to time is small. True or false? Now, an iodine clock it's not really like a clock. It is a reaction. What you do is that you have got two mixtures. Okay, you have got mixture A, and then you have got mixture B. So what happens is that for this one, you get these two guys, you mix them. So we're going to pour one into the other. Okay, what you are doing is mixing. And what you actually see is that Depending with the concentration of the reactants, the color change here is going to become black. Color changes. Initially, the two solutions are colorless, but once you mix them, the mixture is going to become black. But depending with the concentration of the reactants, let's say you have got two experiments. The first one, the concentration of A is 0.5. The second one, the concentration of B is, let's say, 1. So the one where the concentration is 1 is going to quickly change the color to black. The one whose concentration is small, it will take a bit of time for the concentration to change color. You can actually just see a simple tutorial video on YouTube of how this Alden clock is. If they mix, you just see the way the color is changing. Push, the color changes to black when you mix them. So now the question is not asking us really about that, but it's asking about us about the if the time required for color change is too small, then the error with respect to time is this small. Is that true or false? So how do you find percentage error? So percentage error is given by the absolute error divided by the measured value, and then times 100%. So if the time required for color change is too small, what is going to happen? In other words, what does that mean? The time required is too small. It means that the measured time is small. Now, if the denominator is small, what do you think is going to happen to the error? Anyone to answer? If the denominator is small, or let's say you just have a fraction, if the denominator is small, do you expect the entire answer to be big or to be small? Anyone? Let's say you have got 1 over 1 and 1 over 10. This is small, this is big. Between the two numbers or the two fractions, which one is a bigger fraction? Is it where the denominator is small or where the denominator is big?
No.
It's where the denominator is small, isn't it? Very good. Okay. So this is what happens here also. So if the denominator is small, it means that the percentage error is going to be big. So that option which is saying is going to be small is actually false. I hope that's okay. Sorry, just a moment. So here our answer is false. Okay. Because you expect the percentage error to be big if the time is small. The next question is saying nitrating mixture is prepared by adding sulfuric acid to nitric acid with cooling. Cooling is required because reaction is. Now, why do we cool? When you mix the sulfuric acid with nitric acid, this reaction is going to produce heat. That's why you cool it, because you can't cool something if it's not producing heat. So that tells you that this is actually the reaction is exothermic. The reaction is exothermic. Remember exothermic? What happens is that the heat is released. Okay, heat is released. That's why you want to cool. Does that make sense? Okay, I hope it makes sense. Number 9 is saying benzene is harmful by skin absorption. A necessary precaution that is taken is because benzene is harmful. What do you do when you're in the when it's actually harmful by skin absorption? So what are you going to do really to help you with that? Using fume cardboard, wearing gloves, using goggles, wearing a mask. So for this one, when you a fume board is used to help in if you have got a mixture of a gas that is volatile. So you have got a gas, but then this gas, the thing is that it can get to harm you. So you use a fume hood, and why you are using it really is so that as you do the process, that gas is going to be absorbed, okay, so that it cannot injure you. That is the work of a fume hood. But here you are talking about something that is harmful to the skin. And then wearing gloves, this is going to help because when you wear gloves and then your substance is harmful to the hands, it can be absorbed and then it will not be able to harm you. Using goggles is for those that irritate the eyes, and then wearing mask is also for those that really maybe are going to irritate their nose. Okay, they have got a bad smell. Eye protection is one when reactant as are irritant. I already mentioned this, isn't it? Like that's why we wear goggles for things that are irritant to the eyes. 11 is saying the titration reaction involving. Okay, so this one is not showing, but this is supposed to be showing. Let me just double check it. Okay, involving permanganate. This is supposed to be MnO4 minus and iron 2 plus. So this reaction does not require an indicator. As why does this reaction not require an indicator? So when you are reacting ions, this we call it redox titration. Remember the types of titration. You have a back titration, a simple or direct titration, and then a redox titration. In a redox titration, no indicator is required. Why? Because the ions themselves change color, okay, due to ions. The reactants themselves will change color, and that is going to tell you that a reaction is happened. Because in this reaction, what will happen is that ion 2 plus will actually be producing ion 3 plus, and each ion has got its own color, and you'll be able to tell. So the reaction is self-indicating. Number 12 is saying when reading the burette, if the eye is above the liquid level, the resulting volume reading would be too small. True or false? So a burette, something like this. I've got a tap down here for a burette. And then normally the liquid here is going to have a meniscus. Okay. And then the readings, you have got different values that you can read. So I've got the value on this level, let's say is 20. Then you have got a value that is here, let's say is 21. Then you also have a value that is a little lower, let's say is 19. So you're supposed to place your eye here if you are to read the correct thing. If you read from the top, what is going to happen is that you are going to read a higher value. Okay, you might end up reading 21 instead of 20. And then if you read from below, you might be ending up reading a smaller value. So we call these as parallax errors. Parallax errors. The thing is that as you look through a liquid, you are going to have the values changing, or you'll be able, because of refraction, you will be able to see wrongly the values because you are looking through the fluid. So this is false because when you read above, the value is going to look bigger instead of smaller. 13 is saying, in a Bunsen burner, a bright blue cone is observed when the ratio of gas to air in the barrel is too large. True or false? Now, in a Bunsen burner, when the ratio of gas to air in the barrel is too large, like the meaning of this is, let's have, I can show some pictures. So we have got a blue frame, a, this one, you have got a frame which is blue, and then you also have a red one, or considered orange. So what's the difference for these flames that you are going to be able to see as you get to burn your gas? Now, for you to see a blue frame, it means that you have got about equal amount, okay? So the gas and air is equal, they are equal. Like the gas that you are burning and the air. The air here is just representing the oxygen in the atmosphere. So they are equal. That's why you are having that blue flame. And this one is represented when you're having this bright blue cone. It indicates optimal mixture because the gas that you are burning and the air is the same. Okay. And what is happening here is that there is complete combustion. Complete combustion. But when you see this orangish flame, it means that you have got a lot of gas. Okay, gas is greater than the air. Remember, the air basically contains oxygen. So there is actually incomplete combustion. Incomplete combustion. If there is incomplete combustion, you still have some carbon that is not burning there, and that's the one that will be responsible for the car. 14 is saying precision is the reproducibility of the results when several measurements of the same quantity are made. True or false? This one is true, isn't it? What is precision? We can explain precision in a simple way by us using this bullseye. Okay, we can have this scenario we have here. For we'll talk about first something that is precise but not accurate. Precise, not accurate. To be precise just means that repeated measurements are close to each other. You are throwing knives and they're all falling on the same point. You are precise. But you're not accurate because accuracy means hitting the target. And then we can talk about someone that is precise and also accurate. To be accurate means that you hit the middle point here. Okay, so meaning you can't be accurate but you're not precise in this case. Of course, you can be accurate once and then the other times you are just throwing anywhere else. But as long as you've thrown on the middle here, you are accurate. And as long as these things you are throwing are close to each other, you are precise. You can be not precise and not accurate at the same time. Not precise, you throw here, and then you come and hit here, you come and hit here, you come and hit here, you come and hit here. They are not close to each other, so not precise. And then they are not on the middle, so not accurate. And then this was the last question. A sample, so it's an interesting question. You can see that's 15 marks, meaning that if you get everything that you're supposed to get here and then you come and get this one wrong, it's like work done is equal to 0. So a sample of impure magnesium was analyzed by allowing it to react with excess hydrochloric acid solution. After 1.32 grams of the impure metal was treated with 100 cubic centimeters of 0.75 more per cubic decimeter, supposed to be more per cubic decimeter of hydrochloric acid. The remaining solution required 50 cubic centimeters of 0.25 against is more per cubic decimeter. Aqua sodium hydroxide for complete neutralization. Assuming the impurities do not react with the acid, what is the percentage by mass of magnesium in the sample? So you need to analyze what is happening in this question. Okay. So the first thing first, we have got a sample of impure magnesium which was analyzed. So this impure magnesium was reacted with excess hydrochloric acid. So we have got magnesium which reacted with excess hydrochloric acid. Please take note that it's in excess. So what do you think we are going to produce in this reaction when we react the magnesium with the hydrochloric acid? We'll produce magnesium chloride and hydrogen gas. So magnesium chloride and the hydrogen gas. Is this a balanced equation? Not really. To balance it, we'll put a 2 here. Okay. And then we've been told after that, because remember hydrochloric acid was in excess, so meaning that if this reaction happens, the entire magnesium is reacting, but some hydrochloric acid is remaining. And that hydrochloric acid that remained from here is what we're going to go and react with the sodium hydroxide. So we've been told after 1.3 grams of impure metal was treated with 100 cubic centimeters of 0.75 hydrochloric acid. So in other words, let's determine how much of hydrochloric acid reacted with the impure metal, okay, from what we've been given. So we are going to calculate first the initial moles of hydrochloric acid, moles of, how do I even write this? Okay, I can put it as initial moles of HCl. The initial moles of HCl, we've been given the information. We had 0.75 mole per cubic decimeter of 100 cubic centimeters. So we have got, how do you find moles? Moles is concentration times volume. The concentration is 0.75 mole per cubic decimeter. The volume is 100, but this is cubic centimeters. We need to convert this cubic centimeters of volume to cubic decimeters. And how you do that is just by getting this value and dividing it by 1000, or we'll multiply. We have a centimeter on top, centimeter cubed, we'll put a centimeter cubed. We want to go to a decimeter cubed. 1 decimeter cubed has got 1000 centimeter cubed. So if you multiply, you can see the units will cancel. This decimeter cubed will cancel the decimeter cubed, centimeter cubed will cancel the centimeter cubed. Our answer will just be now in moles. If you punch this on the calculator, this is going to give you 0.0125. Okay, let's see. Moles of hydrochloric acid. Okay, that is going to be 0.075. 0.075 moles of hydrochloric acid. So these are the initial moles of hydrochloric acid that we have. Remember, these are the initial ones. What does it mean initial? At the beginning. But remember, at the beginning, hydrochloric acid is in excess. So meaning that not all of these moles will react. Okay? But one thing that we know is that when hydrochloric acid reacts with magnesium, whatever that is going to react will remove, uh, when magnesium reacts with hydrochloric acid, only part of these moles that you can see will be used up. Some of the moles will remain to go and react in the second reaction with sodium hydroxide. So let's now deal with the second part with the sodium hydroxide. So the amount of hydrochloric acid that remains will react with, I'll put here, this guy is in excess. So the amount of hydrochloric acid that remains will react with the sodium hydroxide, and that is going to give us sodium chloride plus water. But we were told that from the question, the remaining solution required 50 cubic centimeters of 0.250 more aqueous sodium hydroxide. So we actually know the amount for sodium hydroxide. It's 50 cubic centimeters of 0.25 more per cubic decimeter. So we can calculate the number of moles of sodium hydroxide here. And these are the moles that reacted with hydrochloric acid. So number of moles of sodium hydroxide that reacted with hydrochloric acid is going to be equal to concentration times volume. The concentration is 0.25 mole per decimeter cubed, or multiplied by the volume, which is 50 cubic centimeters. But let's again convert this value. We have got a cubic centimeter on top, we'll put a cubic centimeter down. We are going to a cubic decimeter. 1 cubic decimeter has got 1,000 cubic centimeters. So this will cancel with that. Decimeter cubed will cancel with this also. So when we punch this on our calculator, it's going to give us 0.0125 moles of sodium hydroxide. Now from the balanced equation, we can determine the number of moles of hydrochloric acid that reacted. The number of moles of hydrochloric acid, look at the coefficient, the number in front is 1. So it's supposed to be number of moles of hydrochloric acid over 1 should be equal to the number of moles of sodium hydroxide also over 1. So this tells us that the number of moles of hydrochloric acid is going to be equal to the number of moles of sodium hydroxide, which is 0.0125 moles. Okay. So these are the moles of hydrochloric acid that reacted in the second equation. But remember, for these moles to react in the second equation, it means that these are the ones that had remained from the first equation. Because when the first equation was done, whatsoever that remained was what reacted in the second equation. So we now find what will be the number of moles of hydrochloric acid that reacted in the first equation. Okay. So, number of moles of hydrochloric acid that reacted in the first equation. So, reacted with what? Reacted with magnesium is going to be the number of moles of hydrochloric acid initially minus the number of moles of hydrochloric acid that reacted with sodium hydroxide. Okay, so the number of moles that were present initially is 0.075. The ones that reacted in the second equation was 0.0125. So if you get to subtract this, 0.075 minus 0.0125, you are going to get 0.0625. 0.0625 moles. So these are the moles of hydrochloric acid that reacted with magnesium. By looking at the balanced equation with magnesium, the number of moles that reacted with magnesium, I mean the number of moles of hydrochloric acid with the number of moles of magnesium, you can see they're in a ratio of 1 to 2 there, isn't it? Okay. So we're going to say the number of moles of magnesium over 1 should be equal to the number of moles of hydrochloric acid over 2, because that's a balanced equation. Because we want to find the number of moles of magnesium that reacted. So number of moles of magnesium over 1 is equal to number of moles of hydrochloric acid over 2. So therefore that to mean that the number of moles of magnesium is going to be equal to 0.0625 over 2, and let's see what that gives us. 0.0625 over 2 give us 0.03125 moles of magnesium. So now let's determine the mass of magnesium that reacted. So the mass of magnesium that reacted is equal to number of moles times molar mass. So the number of moles is 0.03125 moles. The molar mass of magnesium we get from the periodic table, and that is 24.31. This is in grams per mole. So you see the grams, the moles will cancel. If you multiply this, you are going to get 0.760. 0.760 grams of magnesium. So these are the moles of the mass of magnesium that reacted. But remember, magnesium was impure, and we know the mass that was actually reacting. So we had mixed 1.32 grams of impure metal. But remember, this was impure. The question is, what is the percentage by mass of full magnesium that is in the sample? So I want to find the percentage purity. Okay. Or the percentage of magnesium in the metal. So percentage of magnesium is going to be the pure magnesium divided by the amount of impure metal, and then you multiply that by 100%. So the pure one is 0.760 grams. The impure one is 1.32. 1.32 grams, and then you multiply that by 100%, and let's see what that gives us. That is going to give us 57.58. 57.58%. So our answer is there. So that is how you go about this question. In case you want to get registered with us, please feel free to text or call us or WhatsApp us on 0974016268. You can register for us in mathematics, physics, chemistry, and biology. And you'll be able to access all our recorded classes, tutorial sheets, and also past papers. Thank you so